Yes. Hello everyone. So today we are going to introduce a new chapter, especially in organic chemistry. This is most important one, which is reactive intermediates. So reactive intermediates will play an important role in case of organic chemistry. So if you want to predict any organic reaction with a maximum number of chemical reactions, so definitely it should be proceeds with a intermediate. That intermediate is nothing but a reactive intermediate. So keep it in as reactive intermediate. It is also known as reaction intermediate. Many names are there. Some books they will announce as reaction intermediate, otherwise you can say reactive intermediates. So what is a reactive intermediate? How it is used to identify a chemical reaction and how it is possible to predict a chemical reaction, all will be discussed in this one. So generally we know if I take any organic reactions are classified into two types. Generally two types of organic reactions are present. Organic reactions are classified into two types. So first one is concerted reaction, okay, and second one is non-concerted reaction. So we know that organic reactions are two types, concerted reaction and non-concerted reaction. Concerted reaction nothing but a single step reaction. This is called a single step reaction and this is called multi-step reaction. Two types of reactions are there, single step reaction, one more is multi-step reaction. So especially in concerted reaction, a reactant is starts converted to product by a intermediate, okay, this is not a step, and finally that is responsible to give product. But here I am writing one I is nothing but a transition state, so it is not a intermediate in this reaction, okay, it is a transition state. Now A gives rise to one intermediate, now see it is giving a product here now. So now this is a step 1 and this is step 2. Now it is minimum 2 steps are required to identify a intermediate in any reaction. So now this is a single step reaction with a intermediate, that is transition state, and this is a multi-step reaction which is giving a product which is proceeds more than one step. Now this is called a intermediate. With the help of this intermediate we can guess what kind of reaction is going to be established to give this product, okay. Now generally what is a reactive intermediate? So reactive intermediates are, see, the short living organic fragments. The short living organic fragments, how they are produced? They are produced by homolytic and heterolytic fission. Homolytic and heterolytic fission. Homolytic and heterolytic fission. In any organic reaction, if any reaction is proceeds more than one step, definitely one intermediate is going to be established. That intermediate is nothing but a reactive intermediate. Now reactive intermediates are a short living organic fragments that is produced by either homolytic or heterolytic fissions, okay. Now especially these organic intermediates are generally classified into 6 types. 6 types of organic intermediates are there. So here first one is carbocation, second one is carbanion, now third one is free radical, and fourth one is carbene. Now fifth one is nitrene and sixth one is benzene. So these are the 6 possible reactive intermediates which are observed in case of organic reactions. So they are carbocation, carbanion, free radical, carbene, nitrene and benzene. So in case of any named reactions, rearrangements and in any interconversion, definitely these 6 intermediates are most important for your not only cracking examination, it is also helps in research even. So that's why reactive intermediates will play an important role in all chapters starting from GOC, and it is even ends with a spectroscopy also. So these intermediates will play an important role. So now we are going to discuss individual intermediate and what are its characteristics and properties, etc. So for every intermediates, first we will learn about structure. After learning the structure, we learn about how to generate, how to stabilize, then followed by its corresponding detection methods, and finally chemical reactions. So every intermediate's 5 properties we are going to learn. First is its structure, then generation, stability, and one more is detection, means how to identify this intermediate in a chemical reaction, and finally chemical properties of a intermediate. So 5 properties are required for all intermediates. So one of the property already we discussed in GOC, that is stability. So stability I am not going to give complete information in this one. I will explain only 4 properties for individual reactive intermediates. So I would like to start carbocation. So first most intermediate is carbocation. Carbocation. So 5 things we will discuss for every individual reactive intermediates. First one is structure. Structure of a carbocation. Now see, what is a carbocation? Carbocation is a trivalent carbon intermediate. Trivalent carbon intermediate bearing positive charge. Bearing positive charge. Carbon bearing a positive charge, that is known as a carbocation. So valence is 3 and having a positive charge on a carbon, that's why it is called carbocation. Now carbocation is found to be unstable, and this is sexted electronic species. Sexted electronic species. So they carry 6 electrons. That's why it is called sexted, and it is found to be unstable. And see, this molecule is found to be reactive, unstable and reactive, and this is formally positive charge species. Formally positive charge means they carry a positive charge here. So don't miss every point, you keep writing. Well, because this will place an important in case of molecular rearrangements as well as named reactions and individual chapters such as alkane, alkene, etc. So carbocation is reactive, it is formally positive charged, and due to presence of paired arrangement of electrons, it is found to be diamagnetic in nature. Carbocation is diamagnetic in nature. So it is same way, due to presence of positive charge, it is electrophile. Carbocation is electrophile. It is same way, it is behaves as a Lewis acid. It is diamagnetic in nature due to presence of paired arrangement of electron. Carbocation is electrophile. It is also shows a Lewis acid character due to presence of one empty cavity within the molecule. Suppose see, if I take a carbon with 3 valency and here one empty orbital is present bearing with positive charge. Now this is called carbocation bearing positive charge. So this you can also represent in one more way. CH3 and this is plus carbocation. Now if you want to determine hybridization, so it is sp2 hybridized, 3 bond pairs are present, 1, 2, 3, that's why it is sp2 hybridized. Now if you consider the geometry, it is a trigonal planar geometry. It is a trigonal planar geometry and with a bond angle of 120 degrees. So these are the key points regarding a carbocation having a 6 electrons. See, it is a trigonal planar having 6 electrons in their valence shell. So finally we can say that it is 1, 2, 3 sp2 hybridized trigonal planar geometry with a bond angle of 120 degrees. Don't miss any point, you keep writing. So sometimes they will ask a direct straightforward question. So they will give like this. See, carbocation is a diamagnetic in nature. They will give question like this. Diamagnetic in nature, paramagnetic in nature, option C. Now sp3 hybridized skeleton, it is sp3 hybridized skeleton, option D all. Which option is correct for carbocation? Carbocation is a diamagnetic in nature. Okay. So most of the carbocations bearing with a positive charge, that positive charge species are carrying a paired arrangement of electron, even though they bearing a positive charge, but see this molecule having a 6 electrons in their outermost valence shell. So that's why this is becomes a diamagnetic in nature. So you can also expect like this. Bond angle of carbocation. Bond angle of carbocation is dash. Now you may expect either 109 degrees 28 minutes, or we can say 107, option C, that is 120, option D, that is 109 degrees 5 minutes. So already given it is 120 degrees like this. Very sample questions. So this may be very low standard questions. Sometimes suddenly they will ask. So that is about carbocation structure relation. Next is generation. Generation of a carbocation. How to generate a carbocation with the help of some selective reagents. Now in this case, see, I am taking a alkyl halide, this is CH, and here one more CH, and here I am taking a bromine, and in this I am reacting with a polar solvent. Polar solvent means which having some polarity, otherwise you can say which having some dipole moment as well as dielectric constant. So you can take water, methanol, acetic acid, anyone you can use, which is suitable for this molecule. Now carbon halogen undergo heterolytic fission. After heterolytic fission, now see this carbon carry positive charge, that is carbocation. Okay, you can take even phenyl rings around this carbon. Phenyl rings are connected. Now same polar solvent I am using. Remove this and see carbon carry 3 phenyls with positive charge, carbocation. So the common thing is use a suitable solvent which is required for a substrate and try to make a heterolytic fission, you will get a carbocation. Break this bond and create a carbocation every time. Okay, and see one more. I am taking a alkoxy group attaches to halogen. Now use polar solvent, remove this. After removing this, now see, you will get a carbocation. This carbocation is get stabilized by oxygen non-bonding electron. The key concept in this one is every time we need to generate a carbocation. That carbocation may be stabilized by non-bonding pi electrons or sigma electrons, etc. See, this is a allyl carbon. Use a solvent, remove this, and after removing this, now you will get a carbocation. See, every time this is a common thing. We need to generate a carbocation with the help of suitable polar solvent. Okay. Now, not only this, if I take alkyl halide in presence of any heavy metal cation, it may be silver or mercury. So they can remove this chlorine and finally that may generate carbocation. Even acid halides. Acid halides are also reacts with a heavy metal cation. So this may be removed in terms of chloride and reacts with acyl. Okay. Now we know this is very well in case of Friedel-Crafts alkylation reactions and acylation. Remove this chlorine, this will enter here. So after entering here, CS replace and what you will get? AlCl4 minus. With the help of heavy metal cation, silver, mercury, etc., you can take any heavy metal cation bearing positive charge that may take chloride ion from substrate and forms a carbocation. Here also remains same. Acyl forms by taking Ag plus this chlorine and AlCl3. Even Lewis acid also possible. This is called Friedel-Crafts alkylation reaction. So finally, what we are generating now? Carbocation. Next, see, same acid halide is going to react with a Lewis acid. Now what happens? See, this chlorine is removed. After removing this chlorine, you will get a acyl cation which is converts AlCl4 minus like this. This is called Friedel-Crafts alkylation and this is called Friedel-Crafts acylation. By removing this chlorine, you will get acyl. This acyl is substitutes on benzene. That is one more technique. Okay. So I am taking a triphenyl carbon connected with chlorine. Now tin tetrachloride. fourth group element, tin tetrachloride. Now it is also Lewis acid. Now chlorine enter in this one, and see this carbon connected with carbocation, tin pentachloride -1. Now even if you take a organofluorides on reacting with A. So antimony pentafluoride, now this fluorine enter in this one and finally forms R plus. Now antimony hexafluoride -1, etc. So you will get a carbocation as well as carbanion, common constituents if they are having a multiple substitutions. So anion formation takes place, that may be even carbanion bearing a negative charge have a tendency to remove proton. So some cations are formed due to a neutral molecule have a tendency to show its characteristic basic property as well as acidic property. Right now it is a Lewis acid, acidic property, which can have a tendency to remove this fluorine and forms a anion. Okay. Next, even you can take a super acids, CH3 and here it is hydrogen. Now I am taking antimony pentafluoride, next fluorosulfonic acid. This is called superacid. Superacid is that one which can have a mixture of protic acid as well as Lewis acid. So mixture of these two is called superacid. Lewis acid and protic acid is called superacid. Now this can form like this. Antimony pentafluoride, which will lose one of the proton, SO3 -1, it can donate one proton. This proton and this anion and this proton get combined together and forms a hydrogen gas. Hydrogen gas is removed out, and finally this carbon is converted into the form of carbocation like this. H minus donor, H plus donor combines and forms H2 gas. Finally this carbon bearing positive charge. So this is called a superacid. Intermixing a Lewis acid as well as protic acid is known as Lewis acid. Not only this, you can go for any combination. H2SO4 in presence of antimony pentachloride. Use any one. Mostly one protic acid is required and one Lewis acid, that is known as superacid. Take down. Over. Right. Now, so not only this, by taking any alcohol, see this is alcohol, if alcohol takes proton, hydroxy will take this proton here and forms a oxonium ion, H2O plus like this, and this will lose water molecule, and finally there is a formation of a carbocation. Alcohols have a tendency to undergo dehydration under the influence of acid medium. Okay. So take one alcohol and this alcohol will take this proton. So after taking proton forms oxonium that is removed in terms of water. Okay. So this is also possible with a olefin. When olefin takes proton, now we know olefins are nucleophilic in nature. One of the carbon is more nucleophilic and proton will be added to that one which is more nucleophilic. So out of these two carbons you can add proton on any one. Then after adding proton here you will get a carbocation. So if you know this concept, you can understand what is a Markovnikov rule. See, I am taking two unsymmetric olefins, carbon. Now I would like to add this proton on this unsymmetric sp2 carbons. So the key thing is, when I transfer these pi electrons over here, this carbon bearing negative charge, that will take this proton. So after taking proton, definitely inner carbon carry positive charge, which is a most stable carbocation, and later on negative ion. So when you add a proton from this, a negative ion will be there. That negative ion is going to contribute in second step and finally forms a addition product H plus and followed by Cl minus. So this is follows Markovnikov rule. So adding a electrophile on a double bond, that will develop a carbocation. That carbocation after formation, that will take a negative ion, that is called Markovnikov rule. Okay. Even triple bond also follows the same thing, carbon carbon triple bond hydrogen. Now this proton will be added on one of the carbon. If I add here, can I write like this, carbon carbon double bond, and this is CH, and here one hydrogen is added, and this is plus. Why? Because even triple bond is also nucleophilic in nature, so that will take this proton. Okay. Next, suppose if I take a ether, this is ethereal oxygen. When ethereal oxygen takes proton, then see exactly central oxygen will take this. This is CH3 and here it is H and this is plus. Now after formation of oxonium, now between left side, right side two organic parts, which part is going to be cleaved? That is completely depends on stability. So if you cleave this one, this will carry a ethyl carbocation. This ethyl carbocation is more stable than if you break towards right side. So why? Because if you break this side, you may get methyl. Methyl is unstable. Now this bond is very strong and this bond is weak. So strong and this is weak. Remember, whichever organic fragment having a unstable cation whose corresponding bond is very strong, and whichever organic fragment having a stable cation corresponding bond is weak. After adding proton, we need to break that particular carbon oxygen bond, which will give a stable carbocation. Take this. So every time we can generate many cations by adding a proton, by selecting alkene, alkyne, halogens, cycloalkanes, even strained cycloalkanes, and even alkene produced by a cycloalkene, okay, and even alcohols, acids, acid derivatives, etc. Clear? This generations helps in other concepts. Be careful. Write clearly. Now, I am taking a carboxylic acid. Even carboxylic acid have a tendency to take proton from more acidic molecule. So this will take proton. After taking proton, there is oxonium ion formation takes place, loss of water, and finally your answer is formation of acyl cation. So this kind of reaction is possible only when it is coming from an acid whose acidity is very stronger than aromatic or aliphatic carboxylic acids. Then only there is a loss of water molecule takes place from this. Now it is acts as an acid, now it is acts as a base. Even carboxylic acids undergo dehydration. So not only this, even I can take a ester. See, this is one ester. After adding proton, you may take this. This lone pair will take that proton. After taking proton, now there is oxonium ion formation takes place. Remove this. After removing this, finally see there is a formation of acyl cation, and see there is formation of methanol. Even esters also have a tendency to take proton from corresponding acid centers and forms a acyl cation. Okay. Next we can also take anhydride. This is one anhydride. Now anhydride have a tendency to take proton. Now this will take proton. After taking proton, this anhydride have a tendency to remove like this. See, this is the anhydride. Now this will lose acyl cation. After losing acyl cation, now there is formation of a acetic acid. Why? Because it is a dehydration product. This molecule is a dehydration product. So when dehydration product, if they have any tendency to take proton, they may leave one carboxylic acid and forms acyl cation. Right. Many ways we can generate carbocation by influencing a polar organic molecule starting from alkane. Clear? Now, I am taking a cyclopropyl methyl attaches to alcohol. So, this is after taking proton, this oxygen will take proton and see this is CH2 H2O plus, right. So, after getting this, now this will lose water molecule. So, after losing water molecule, you will get CPM cation. This is called cyclopropyl methyl carbocation. So, this may undergo ring expansion, otherwise it may also take incoming nucleophile directly. That depends upon the source which is coming. Suppose if they undergo ring expansion, so now see, you may get a 4-membered ring, that is the answer. So, intermediate is carbocation. Clear? Next, suppose if I take cyclohexene on taking proton, this will migrate out. After taking this, now see, here will expect proton and proton will be added on this carbon. Now, this becomes a carbocation. Many ways you can generate by removing corresponding unsaturation. After addition of this proton, you will get a carbocation. Clear? Next. See. Now, see, I am using a nitrous acid. This is amine, and here I am using a nitrous acid. When nitrous acid reacts with amine, then amine is get converted to diazonium, nitrogen triple bond, and this one. This is on heating, N2 will be removed out. After removing this N2, now you will get a carbocation. So, first what we are converting? We are converting amine into diazonium. Under thermal condition, diazonium loses N2 and forms a carbocation like this. Not only this, we know very well, benzene is a nucleophilic in nature that can accept a electrophile. Now, this electrophile is going to be added on benzene. This electrophile is added on this benzene. Why? Because benzene is a electron rich center or nucleophilic in nature. So, this carbon carry 2 electrons and becomes a negative ion. That negative ion takes this electrophile and here you will get positive charge. So, that is why benzene undergo electrophilic addition followed by substitution. Finally, we can say electrophilic substitution reaction. Substitution reaction we are saying EPS. So, this is well known. Suppose see, if I use a alkyl halide, otherwise you can say methyl cation, and can I say acyl cation? This is acyl cation. Using methyl, nothing but a alkylation, Freyl-Craft alkylation. Now, this is acylation, okay? And you can use nitronium, nitro, everywhere you can use. Any kind of electrophile if you add on benzene, then what happens, see, one of the electrophile is added over here. This is electrophile, that is CH3, and here you will get positive charge. Suppose if I take a acyl, that acyl group is added over here. This is C double bond and this is plus. And finally, that may loses proton and forms aromatic molecule. So, this is an example of Freyl-Craft alkylation reactions. Clear? Yes, you can. Now, see, I am taking a carbocation. Carbocation have a tendency to generate other carbocation. See, this is a hydrocarbon part which carry hydrogen. Now, it is a carbon bearing positive charge with 3 phenyl. Now, this can have a tendency to take this proton. Now, this hydrogen migrates from this carbon to here. After getting this, what happens? See, you may get a tropylium. This is tropylium. Now, one cation responsible to generate other cation. This is possible only when initially used carbocation is found to be stable, then formed carbocation. So, reactant carbocation should be unstable, then formed carbocation, then only this kind of reactions are possible. Okay. Suppose, see, if I take ethyl carbocation next is connected to, now here hydrogen is connected to one more, this one. Now, whether this reaction possible or not, they may ask in exam. Now, how to write? Remove this hydrogen and add here. After adding, you may get a alkane. Now, what about this carbon? This carbon becomes a carbocation like this. So, based on this, we can say that the used carbocation should be unstable, then formed carbocation, then only the reactions are possible. Okay. Suppose, see, this is one more example I will give. CH2 plus, then C, I am using a tertiary carbon. This is tertiary carbon. Suppose if this hydrogen migrates from here to here, then what happens? You may get a hydrocarbon. Now, you will get a carbocation like this. This is one carbocation. If you observe this clearly, this hydrogen migrating from this carbon to this one, it is initially used carbocation as a reactant. Now, this hydrogen, if it is migrate, you will get a one more carbocation. Is this formed carbocation is more stable than this one or not? Is it more stable? No. Why? Because benzyl is more stable as compared to tertiary. So, that is why this reaction is not exist. Always remember, we need to choose a cation which should be highly unstable than formed carbocation. Only that reactions are possible. Okay. So, one more example I will give, just you concentrate. This is CH3. Next, I am using a tertiary or secondary carbocation. See, this is one. Now, whether this reaction exists or not. If this will take H minus ion from here, now what kind of carbocation you will get? CH2 and this is plus, and see, this carry CH3, CH2 and here one more CH3, that is propane. So, is it reaction possible or not? Yes. Why? Because used carbocation is unstable, formed carbocation is more stable, that is the reason. This strategy is very, very important. So, in your examination, 4 options they will give and they will ask which among the following reactions exist. On that time you can choose this. So, that are generations are over. All possible generations are given in variable organic functional groups starting from alkane, olefin, triple bond, halogen derivative, alcohol, acids, esters, etc. So, this kind of questions are most common. They will take one unstable cation, and if they prepare a stable cation, only that reaction exists. Out of 4 options, you need to choose which is correct. Next, after generations, next most is detection of a carbocation and stability. So, that is your third application. Third application of carbocation is stability. This already explained, just go through GOC. Now, always remember, carbocation stability always depends upon donor. Why? Because it is electron deficient species. Primary, secondary, one more I am taking, that is tertiary. This application is already given, just go through GOC. I am giving sample one example. Now, methyl having one donor, here 2 donors are there, now here 3 donors are there. Which is more stable? Fourth one is more stable than third one, second one and first one. If donors are present, stability increases. And what about if withdrawing groups are present? When withdrawing groups are present, stability decreases. See, this is one carbocation having a nitro. Now which is more stable? First one is more stable than second one. Why? Because here donor is there, but what about here? Withdrawing group. Suppose if nitros are increases, this is CH2 plus, this is CH and this is NO2. Here NO2 and this is plus. Now 3 nitros I am taking around carbon. When carbon bearing 3 nitro, it is found to be unstable. Why? Because it is a withdrawing group. As number of withdrawing groups increases, stability decreases. So can I say first one is little bit better than second and third? Yes. And one more. Regarding carbocation, already one point explained. Conjugate carbocations are more stable. Now here 2 conjugations are there and here 3 conjugations are there. As number of conjugations increases, stability increases. This point also already explained. Okay. And if any carbocation stabilized by non-bonding electron, whose stability is very high as compared to pi electron stability, sigma electron stability. Now see, this is stabilized by non-bonding electron. This is stabilized by pi electron. Next, this carbon bearing positive charge is stabilized by only donor. Non-bonding electrons will stabilize this. Here pi electrons will stabilize this. Always non-bonding electrons are more energetic as compared to pi, followed by sigma. So can I say first one is more stable than second one and third one? Yes. Just revise the applications which are already given in case of GOC of carbocation. So just go through it. There I will explain in inductive effect as well as mesomeric effect. All applications already explained. This I am giving only sample examples. Just to concentrate. Always non-bonding electrons, carbocation is more stable than carbocation stabilized by pi, carbocation stabilized by inductive effect. In GOC, many applications, many miscellaneous applications already explained regarding cation stability, anion stability, radical stability. So we should not discuss one more time over here. Just take examples, and many examples are already available in case of GOC. Just go through it. Why? Because carbocation is a electron deficient, gets stabilized by electron donating groups. That is the reason. Next, detection. How to trap a carbocation or how to identify a carbocation. Clear? Right. How to trap a carbocation. See, if you take carbocation, carbocation is trapped or identified by. So they are identified by, carbocations are identified by HNMR spectroscopy, and one more is mass spectrometry. With the help of mass spectrometry, HNMR, we can identify or trap a carbocation. Especially in mass spectrometry, see, if I take CH3 plus, it is calculated by M by Z, mass by valency or mass by charge. So what is the charge present on carbocation? 1 plus 1 means you should write 1 here. If it is plus 2, write 2 here. So every carbon 12, every hydrogen 1. So can I say 15 by 1? 15 by 1 means it is 15. 12 plus 3, 15. Actually you should write 12 plus 3, 15 by 1 is equal to 15. What this 1 indicates? Charge present on carbocation. Mass by charge ratio. Mass by charge ratio, this will come one more time in mass spectrometry. Right now you remember only one point. Carbon mass is 12, hydrogen is 1, 12 plus 3, 15, and here mass by charge is plus 1, that will be written here finally 15. And you can also calculate a carbocation produced by ethyl. Now can I calculate M by Z value of this one? 12 plus 12, 24 plus 5. So now it is 29. And if I take isopropyl cation. This is CH3 in this one. What about MZ value? Those who are sitting back, you try to say the answer. Is it right? 1, 2, 3, 36, 37, 40, 43. Right, very good, 43. So, one common point you need to identify by watching these examples. If you observe clearly, every time one carbon I am increasing or not, 14 unit is increasing. From year to year, one carbon. From year to year, one more carbon. From year to year, one more carbon. So, can I say 15 plus 14, 29, 29 plus 14, 43, 43 plus 14, 57. So, this is M by Z value. Mass by charge ratio. Okay. And can you give M by Z value of a phenyl cation? So, I am giving directly, that is 71. Right. Each and every carbon, 6 carbons are there. 6 into 12. Just make a calculation. Then finally, so every carbon carry 71 or 72. Just make a calculation. Is it right? 6 carbons are present, 6 into 12. 72. 73, 74, 75, 76, 77. So, now value is 77. 78 is benzene. If you remove one hydrogen, you will get this one. 1, 2, 3, 4, 5, 6. 6 carbons are there. 12 into 6. 72. 73, 74, 75, 76, 77. Like that. And if I take a tropylium and benzyl having same value. So, here it is M by Z value is, can you say 91 or 92? 91. So, to this we need to add a selective calculations of carbons. So, from year to year CH2 is differ or not. So, one of the carbon atom is different from here with 2 hydrogens. So, finally 77 plus 14, 91. Now, this value and this value both are same. See, carbocations now we are detecting by positive mass spectrometry. M by Z value is 91. So, these two are easily interconvertible. Scrambling with the help of mass spectrometry, scrambling of this will give tropylium. So, then 91, 65, 39 like that common fragments are expected. This you will clearly understand in mass spectrometry. But right now our concept is how to identify a carbocation with the help of mass spectrometry. Now, by using HNMR evidence is also there. HNMR evidence. Suppose if I take a carbon bearing 3 methyl groups, here fluorine atom is present, right? After fluorine, sulfur dioxide, antimony pentafluoride is given. Now, fluorine is removed, this fluorine enter here. Now, after removing this carbon carry positive charge. Can I write like this? Now, we know when fluorine is withdrawing electron, this carbon having withdrawing capacity is absorbed by this fluorine. Now, here chemical shift value is 1.35 ppm delta value. And when fluorine converted to, after losing fluorine on this carbon converted to carbocation. Now, carbocation withdraw electron from this carbon. Now, hydrogen loses some electron density. Now, this value will be 4.35 ppm. 4.3545 like that you can write, nothing will happen. So, first fraction, second fraction, if it is any difference, nothing will happen. Even this starting number also having a range that depends on molecule and solvent. So, if you observe clearly, when fluorine connected to this carbon, now this carbon connected to this with hydrogen 1.35. If fluorine replaced by cation, now value is 4.35, rapidly increases, which indicates carbocation is a strongest withdrawing group as compared to fluorine, especially on this carbon. So, when value suddenly ranges from 1.35 to 4.35 means definitely there is a formation of a carbocation. This is HNMR evidence. Now, I am taking one more example with 2 different types of hydrogens. Here one hydrogen and this is fluorine. Now, this carbon having hydrogen, but here there is no hydrogen. So, if you see this one, this value is very higher value. So, 1.45 ppm or 1.43. Now, this value becomes, it is very high. So, 4.64 ppm, 4.64 ppm without removing hydrogen. But here see, when fluorine connected to this carbon, 1.35, right now 1.45, value increases. Why? Because one methyl is replaced. Now if I use same reagent, sulfur dioxide, antimony, pentafluoride, see, this carbon becomes a carbocation and here hydrogen is available. Now these values are completely affected, very higher values are expected now. Here this becomes, so now it is 4.64, now it is 1. Sorry, just make a correction. Just see, how much value is present on this carbon, hydrocarbon? 1.35. So 1.35 means now it is 1.46 ppm. Okay, now see, this methyl value is 1.35, now it is 1.46, just make a correction. Now here see, this value is very high, 1.64 ppm. 1.64 ppm. As compared to this methyl hydrogen value is very high. Now we are calculating only hydrogen value. So later on if I remove, this value and this value is highly differ. Now we can say 13.5 ppm. 13.5 ppm. Now this becomes 5.06 ppm. Delta value. These all are delta. So when carbocation directly connected to hydrogen whose value is very high, if carbocation connected to carbon which carry hydrogen whose value is 5.06. Now initial how much you are getting? 4.35. This and this both are same, but one of the methyl group replaced with hydrogen, then definitely chemical shift value also influenced. So that is HNMR evidence. So many examples you will see in HNMR, how a carbocation shows higher value by replacing fluorine. So normally when halogens are present on this carbon, value will be in the range of below 2 only, 1.4345. So if fluorine replaced by chlorine, bromine, iodine, value still it is less than 1.46. So you may expect even 1.12, 0.9, etc. But suddenly see, if this carbon becomes a carbocation, value increases, which means definitely carbocation can be trapped very easily in HNMR. Write neatly, don't write any mistakes. So if you write any mistakes, so whenever if you are preparing, during preparation you may get a clumsy character of the corresponding concepts. Clumsy character nothing but you will confuse regarding inductive effects as well as mesomeric effect. So that's why write neatly, wherever there is a requirement of key point, that point you try to underline. Underline the key points so that you may get more clarity. So this is last one. Detection is over. Then finally, we need to learn about chemical reactions of carbocation. First we learn structure, generation, then stability, detection, finally chemical reactions. This is last one in case of carbocation. So what kind of chemical reactions you will expect for a carbocation? So generally carbocation involve in two types of reactions. So first one is addition of a nucleophile. Second one is deprotonation. Addition of nucleophile and deprotonation reaction. Only two possible reactions are expected. When you generate a carbocation, that carbocation have a tendency to accept a nucleophile, and one more, they may also undergo deprotonation reaction. So which reaction is possible? It is completely depends on nature of reagent. It depends on reagent. Carbocation generally involve in two types of reaction, addition as well as deprotonation, that is completely depends on nature of reagent. So before this, always remember carbocation also undergo rearrangement reaction. They also undergo rearrangement reaction. Most probably Wagner-Medvin rearrangement, not Wolff rearrangement, Wagner-Medvin rearrangement. So every time 2 points you need to remember. First, carbocation have a tendency to involve in rearrangement or not. After rearrangement, then possibility to undergo addition or deprotonation. So this is also called elimination. So remember, they may undergo addition reaction, otherwise elimination reaction, depends on nature of reagent. First is rearrangement. Always remember, first you check whether rearrangement is possible for a generated carbocation or not. Rearrangement. Later on, you try to write a addition product or elimination product. Remember these 2 points. First you check whether carbocation have a tendency to undergo rearrangement or not after generation. After rearrangement possibility, then only they may undergo addition or elimination. So rearrangement takes place always from after generation of carbocation. See, after generation of carbocation, molecule involve in rearrangement. Molecule have a tendency to involve in rearrangement, especially this should consider unstable to stable cation. Unstable to stable carbocation. So rearrangement always possible from unstable to stable. Don't try to create stable to unstable. Suppose if already you are getting a stable carbocation, then don't go for rearrangement. Why? Because it will give a unstable carbocation. Rearrangement possible only when unstable carbocation becomes a stable during migration of any atom or group. So only that case possible. First, every time you remember one common point. Generate a carbocation, see whether they undergo rearrangement or not, then followed by addition and elimination. So only two reactions, but the two reactions also having exception regarding rearrangement. So the generated carbocation may undergo rearrangement or not, that depends upon the formed carbocation. Okay. Now see one example, you will clearly understand. See, I am using a tertiary butyl carbon attaches to chlorine. Now I am using aqueous potassium hydroxide. It is a nucleophile. Potassium hydroxide is a nucleophile. First it will loses chlorine. After losing chlorine, what happens? See, you will get a carbocation. This carbocation is more stable. Why? Because there is no other alternative to get more stable than this by migrating from here to here like that. So now this OH minus ion is a nucleophile, directly attacks on this carbon. Directly I am writing this carbocation influenced by this one. Can I write hydroxy group replaces or not? Yes. This is SN1 reaction. So chemical reactions of carbocation, remember, first is rearrangement, later on addition and elimination. Whether they undergo addition, elimination depends only on type of reagent. So same molecule, remember, I am repeating by changing the reagent. Now this is chlorine. Now I am using alcoholic potassium hydroxide. That is aqueous, now it is alcoholic. Now it is a basic reagent. First chlorine is removed. Now first step is remain same. This is CH3 and this is plus. Then OH minus. Now it is basic in nature. This will take this proton and this will migrate out. So this will migrate out. Now you will get a olefin. So can I write like this? Carbon with CH3 and here carbon double bond. See the difference. First chlorine is removed, you will get carbocation. Here also chlorine is removed, you will get carbocation. Later on, this OH minus as a nucleophile will attack. Now here also same. This OH minus as a base, it will attack and forms a double bond. Now thing is, this is a addition reaction and this is a elimination reaction. Now, is there any possibility of showing rearrangement? No. Why? Because the formed carbocation is more stable in this one. Now, I am using one more. This is CH3, CH3, CH2Cl. Now, aqueous potassium hydroxide. Remove this chlorine and you will get a carbocation. After getting carbocation, now see this methyl migrates from here to here. Why migration taking place? See why rearrangement is taking place here. This is 1 and this is 2. After rearrangement we can say 1 comma 2. Now to this cation this anion is migrating. So that's why it is called anisotropic rearrangement. Now this methyl migrating in the form of anion. It is migrates from first carbon to second carbon. Why this migration is possible? This migration is possible. Why? Because of only one reason. It is giving a unstable cation to stable cation. Now primary becomes a tertiary. Now it is possible. This is called Wagner-Melvin rearrangement. Every time you need to check like this. So after that I am using aqueous potassium hydroxide. So now OH minus is a nucleophile. This nucleophile directly attacks here and finally you may get this answer. Now this is the answer. Now suppose if I use or else in this case if I use alcoholic potassium hydroxide. Now this is a basic in nature. This will take proton from this adjacent carbocations. Now see this carbon carries CH3, CH3 and this is CH2. Now try to remove from that adjacent carbon of this carbocation which carry less number of hydrogens. This carry less number of hydrogens. So here one of the hydrogen I am removing like this. So if you remove this hydrogen, you will get carbon-carbon double bond and this is one more CH3. This is called Sage-Jeffs rule. After removing this hydrogen you will get a double bond. This double bond is heavily substituted. More substituted double bond is product here. So you can use this one, but that is Hoffman product. Hoffman product is thermodynamically controlled. So that is not major. Now Sage-Jeffs product is thermodynamically controlled. You will get highly substituted olefin. So this reagent helps to make a addition reaction and this reagent will helps to make a elimination reaction. So this is addition, this is addition and from here it is elimination. So first you check whether it is possibility to have a tendency to show rearrangement or not. After rearrangement go through either addition reaction or elimination reaction. Take one more. Tertiary alkyl halide is given. Now if you observe this example clearly, first you identify whether rearrangement is possible or not. That is first thing. Here I am giving pH and this is chlorine. Now I am using a nucleophilic reagent, addition reaction. So if I remove this chlorine, after removing this chlorine you will get a benzyl cation. Remember this. Now you will get benzyl cation. After benzyl cation, can I use this nucleophile directly? Otherwise, can I make any rearrangement? So rearrangement is not exist. Why? Because if I migrate this methyl group here, you will get tertiary. So that's why no rearrangement, directly attack here. So after attacking, what is the answer? This is CH3 and here one more CH3 and this is pH and this is OH. That is the answer. every time generate a carbocation, see whether rearrangement is possible or not, then go for addition or elimination reaction. Addition or elimination. So you can also proceed like this. See, this is methyl and here hydroxy group is present. Dehydration of alcohol is a elimination reaction. Now I am using H2SO4. After H2SO4 you will get protonation on alcohol. After alcohol protonation there is a loss of water molecule is observed. After loss of water molecule, see, you will get carbocation. Is it stable? So we can migrate a hydrogen from here to here. After migration, see, you will get a carbocation. After formation of carbocation, then apply Sage-Jeffs rule. Use either this hydrogen or this hydrogen, remove this, and finally see, you may get double bond. So we are writing double bond below direction or above direction. Don't write outside. Why? Because if you write outside, that is not a Sage-Jeffs product. So dehydration, dehydrohalogenation, okay. So then followed by dehalogenation, all are elimination reactions. So dehydration under acid medium is a elimination reaction. Now this is one more example. So what is the product involved in this one? If I use H2SO4. Now can I add a proton on alcohol? Yes. Add a proton, right? Then remove water molecule. Remove water molecule. After removing water molecule, you get carbocation. Then see whether it is stable or not. If it is stable, you can write directly elimination product over there, but it is not stable, have a tendency to rearrangement. Go for rearrangement and you will get a carbocation. Now, what would like to remove proton? So can I remove hydrogen from here? Now here hydrogen, here hydrogen, here hydrogen is there. Remove this one so that you may get more substituted olefin. Here I am taking phenyl and this is one more, this is CH3. If I use H2SO4 I am using, can I remove that water molecule? After removing water molecule, see, this is H2O plus you will get. Remove this and after removing this, you may get a stable carbocation. This is benzyl. This is benzyl cation. Now from this side, I would like to remove hydrogen. Can I remove from right side? Yes. Remove this and migrate here. So after migration, see, you may get a double bond. Now that is more substituted olefin. Now this double bond should be closer to conjugate group, otherwise it should be more substituted like this. So every time while you are reacting with a carbocation, or if carbocation is an intermediate in any chemical reaction, first you see whether it is possible to undergo rearrangement or not. After rearrangement only, our reagent will participate. So first generate a carbocation, choose whether they undergo rearrangement or not. If it is not undergo rearrangement, attack from there itself. If it is undergo rearrangement to give stable carbocation, then go for that particular direction and attack a nucleophile. That is the answer. Right. So next, see if I take a benzene, we know benzene involved in electrophilic substitution reaction in presence of alkyl halide and Lewis acid. Now what is the answer you will expect here? What is A? So already this I given already in generations of a carbocation. When alkyl halide reacts with Lewis acid, what happens? See. So when Lewis acid reacts with this alkyl halide, first it may undergo loss of AlCl4 minus and cation. Now this cation is primary, have a tendency to undergo rearrangement by using these hydrogens. After rearrangement you will get a secondary carbocation. We know secondary carbocation is more stable than primary, that's why this undergo this kind of rearrangement. After rearrangement only, this cation is going to add on benzene. So that will be added here. After adding this, you may get a isopropyl. Now here you will get a positive charge. Like this, it will attack. Now here this hydrogen is removed in terms of H plus, and finally you may get isopropyl benzene. This is the answer. So you can also write like this, isopropyl benzene. That is final answer. Formation of isopropyl benzene is major product in this one. So don't prepare like this. Suppose if you don't know the concept of rearrangement, generally you will write like this, 1, 2, 3. So this is wrong, this is correct. Why? Because when alkyl halide reacts with Lewis acid, there is a formation of an ionic pair. In this ionic pair, this positive charge undergo rearrangement. Why? Because it is a primary, now it becomes a secondary. Primary carbocation becomes a secondary carbocation due to 1,2 hydration shift. This is called Wagner-Mervin rearrangement. After Wagner-Mervin rearrangement, the newly formed carbocation will attack on benzene, finally forms a hydrocarbon. So everywhere it will follow. Some selective named reactions will follow electrophilic substitution. Electrophilic substitution nothing but addition and elimination. Addition, elimination nothing but substitution. Clear? Yes. One more, this is well known. This is called 1,2 ditertiary alcohol in presence of H2SO4, pinacol-pinaclone rearrangement. Now in pinacol-pinaclone rearrangement, this hydroxy is removed, and C, you may get a tertiary butyl, and this is carnite. This is the answer. Now if you see the mechanism in this one, you will understand by removing hydroxy group while reacting with a proton. Now this proton added on this hydroxy, after adding here you may get H2O plus, and this is hydroxy group. Remove this hydroxy, after removing this you will get carbocation and your hydroxy group is present. Now what happens, you will get tertiary. Now this methyl migration takes place here. This is called 1,2 anisotropic rearrangement. After 1,2 anisotropic rearrangement, now this carbon already 2 methyls are there. If this methyl migrates, you will get 3. Now this becomes carbocation which is adjacent to oxygen. Oxygen lone pair of electrons are stabilizes this carbocation. We know carbocations are get stabilized by releasing groups, pi electrons as well as non-bonding electrons. Now non-bonding electrons are effectively stabilize this cation, that's why it is undergoing rearrangement. So this is a example of Wagner-Mervin rearrangement. At the same way, anisotropic rearrangement, migrating from first carbon to second carbon. It is a origin, it is terminus. Initially this carbon carry 2 methyls. Now if this methyl migrates, you will get 3. Now this will donates one of the lone pair of electron and forms carbocation This carbocation will give oxonium, that may loses proton, and see, you may get pinacolone. So pinacolone rearrangement follows with a carbocation intermediate, unstable to stable. This is key point in this one. Clear? Next. Freyl-Craft alkylation, Freyl-Craft acylation reactions proceeds with a carbocation intermediate. Okay. Not only this, even pinacol-pinacolone rearrangement, some named reactions, rearrangement reactions also proceeds with a carbocation as an intermediate. So one more example, see, if I take a allyl carbon, this is allyl carbon, here I am using chlorine. If I use AlCl3, now this chlorine will take by Lewis acid and forms a allyl cation. Now this allyl cation followed by AlCl4 minus you will write. After writing like this, see, this double bond is a primary allyl. So primary allyl undergo rearrangement. After rearrangement, what happens, see, you may get a stable allyl carbon. So if this double bond migrate here, this carbon becomes a cation. So this is called stable allyl cation. Now from aluminium tetrachloride, one of the chloride ion is attacks from here, and see that chlorine rearranges from terminal carbon to internal carbon. So this is called allylic rearrangement. So initially chlorine present on first carbon, now this is called allyl carbon. After removing chlorine by Lewis acid, you will get a allyl cation. Now this allyl cation gets stabilized by this double bond and you will get a more stable allyl cation. So after removing, you will get an unstable cation. Now it becomes a stable cation. Then this chloride ion attacks from aluminium tetrachloride, and finally you will get allylic rearrangement. This is an example of allylic rearrangement, one of the rearrangement. Okay. Even we can also proceed with a acyl. See, if I take acyl chloride in presence of AlCl3, Freyl-Craft alkylation. Now it is acylation. Last case I given alkylation, now acylation. See, this is the answer. See this, just we remove this chlorine and this part we are adding on benzene. If you see the mechanism, first I am taking a acid chloride on treatment with AlCl3. Now one chlorine atom is entering here. After entering chlorine atom, now what happens, you will get acyl cation plus AlCl4 minus. Observe this clearly. Now the formed acyl cation is get stabilized by non-bonding electron. It is highly stable. See here, there is a positive charge is appeared. Now it is stabilized by non-bonding electron. See this. This non-bonding electron stabilizes this cation, and finally carbon-carbon triple bond. Now this is plus. This is highly stable. Because of this cation stabilized by non-bonding electron, this molecule is highly stable. So after getting this stable cation, it is influenced by a benzene pi electron. See, this is benzene pi electron. This is CH3, carbon-carbon triple bond O plus. Now these pi electrons will attack on this carbon, these pi electrons migrate on oxygen, oxygen get neutral charge. So after getting neutral charge, C double bond O CH3, and this is positive. Later on this hydrogen undergo elimination, and finally you may get double bond. So double bond, this is C double bond O CH3, that is the answer. So there is a loss of H plus ion. This is called Freyl-Craft acylation, proceeds with a cation as intermediate. Allylic rearrangement proceeds with a cation intermediate. Pinacol-pinacolone proceeds with a cation intermediate. Alkylation proceeds with a cation intermediate. Any dehydration reaction, dehalogenation reaction, elimination reactions also proceeds with a stable carbocation. Every time check whether they undergo rearrangement or not. After rearrangement, try to involve reagent effect. So don't involve reagent effect if there is a possibility of showing rearrangement. So this allylic rearrangement possible only when if this cation after participating resonance with this pi electron, you will get a cation. This cation should be more stable than this one. Then only allylic rearrangement is possible, but normally they won't exist. So that is carbocation. Carbocation intermediate is over. So we learn about carbocation with a structure, generation, detection, and finally stability, and at last chemical reactions. So chemical reactions are most important. Why? Because in chemical reactions only we will learn generation as well as chemical reactions. Once if you know how to generate, then you can easily predict what are its chemical reaction. So always remember, first is rearrangement. It may be any kind of, it may be addition or elimination. First is rearrangement. Later on they may undergo elimination or addition reaction. Now take some questions. See, identify following reaction. Just identify the following reaction. See, here I am using a alcohol. Now after using H plus, here you may get this one, you will get double bond. Now my question is, this is a addition reaction, elimination reaction, C, substitution reaction, option D, pericyclic reaction. What kind of reaction it is? What kind of reaction it is? Identify following reaction. Just now only I given one mechanism, based on that you can say. Now remove this hydroxy, we are adding proton, we remove, then this methyl migrates here. Finally we are removing water molecule or not. So it is an example of elimination. Now same, repeat, identify following reaction, like that intermediate reactions they may give. Now this is cation and here I am putting double bond. So what is this? Addition, B substitution, elimination. Elimination, option D, none. So this is not a normal elimination, rearrangement followed by elimination. See, we are migrating this methyl, here we will get positive, here this hydrogen we removed, and this is the answer. Same elimination reaction. Now repeat same question. Identify following reaction. Identify following reaction. See, I am giving a acyl group, isopropyl I given. Now here there is a positive charge is present. Now I remove this hydrogen and finally I created this. So but normally in your examination they will not mention the arrow, they will give like this only. They won't highlight this hydrogen even. So it is an example of addition, elimination, substitution, pericyclic reaction. So now after getting carbocation we are removing hydrogen from here. So now it is also an example of elimination reaction. Very simple reactions. So this is last question. Identify following reaction. Identify following reaction. So I am taking benzene, I am taking alkyl halide AlCl3. Now finally see, you may get a alkyl group on benzene. So it is an example of addition, P substitution, C elimination, option D pericyclic reaction. What kind of reaction it is? Alkyl halide reacts with aluminum trichloride. So you will get a carbocation. That carbocation add on benzene, that is addition. Then hydrogen will be removed like this. So addition, elimination, simultaneously known as substitution. It is electrophilic substitution reaction. See, intermediate involving, take one more, intermediate involving pinacolic rearrangement. See, pinacol, pinacolone rearrangement, pinacolic rearrangement, both are same. Sometimes they will say pinacol, pinacolone, sometimes they will say pinacolic rearrangement. So what is the intermediate observed in pinacolic rearrangement? Carbanion, B. Carbocation, C. Free radical, then option D, carbene. Carbene. So what is the intermediate involved in pinacolic rearrangement? So if you know mechanism, then only possible to predict. Already explained. So it is proceeds with a carbocation intermediate. Pinacolic rearrangement is an example of unstable carbocation to stable carbocation, finally alcohol converted to ketone. That's why it is called pinacolone. Pinacolone nothing but a carbonyl compound only. Okay. So that is end of carbocation intermediate. So some more additional applications are there. You can understand after knowing other reactive intermediates. So after that I will explain some more linked reactions with carbocation. So right now only these are sufficient. Complete information given. So we learn carbocation generations, structure, detections, and one more is trapping. Trapping is important. So why? Because if you know HNMR clearly, then only it is possible to predict. Then at last chemical reactions. In chemical reactions what we learn is how to show a rearrangement, then followed by addition and elimination reactions. Okay. So that is end of carbocation. So in your next class we will discuss your second intermediate, that is carbanion. Okay. We will stop here. We will continue in your next class. Thank you.